essentially ensuring the proper continuity of F and G, right? We would know that we have uniform convergence, right, by plugging the solution back in and putting bounds on the coefficients, right, using something like a Weierstrass M-test. So we have a way of constructing a solution, okay? Another question might be, is this solution unique, okay? Well, we need some energy estimate, okay? Can we do that for this problem? This is a nice problem to sort of extend the approach of computing energy estimates, okay? And so if we define the energy as we have before, right? E of t is equal to a half the integral of u sub t squared plus c squared k of x, u sub x squared dx, okay? And we're going to check conservation, okay? So basically, for two solutions, okay, call them U1 and U2, okay? Take W equal to U1 minus U2. And what do we have? We have WTT is equal to C squared K of X, W X, X, right, just by linearity. We also have that W of 0t is equal to W of 1t, again by linearity. Equal to 0. Right, this is for t greater than 0, x from 0 to 1. This is for t greater than 0. Okay. And we also have that W of x0 is equivalent to WT of x0 is equivalent to 0 for x on 0. Okay. All right. So what's the usual program for checking uniqueness? Well, we take our energy function, right, for this, right? And so E of t, in this case, let's just be clear that we're using WT squared plus C squared K of X, WX squared dx, right? And we'll differentiate that. So what we find is that ddt of E of t, in this case, is going to be the integral from 0 to 1 of WTT, right? Plus, what? Well, we take a look at this, right? And this doesn't involve t, this does. So we just have c squared k of x, wxt, wx, integrated with respect to x, right? We can integrate by parts. To get just the integral from 0 to 1 of WTT integrated with respect to x, okay? Now, if I integrate up just this part here, and I differentiate the remaining part, right, I'm going to get WT K of x, WX with the c squared up front, integral, or evaluated from 0 to 1, minus the integral from 0 to 1 of WT, c squared, K of x, WX, differentiated with respect to x. Okay. So on the boundary, right, w sub t of 0t is equal to 0, and w sub t of 1t is equal to 0, right? Because w 0t and w 1t are equal to 0. Okay, so that means this whole thing goes away, right? This has wt out in front, and then I have wtt minus c squared k of x wxx dx, right? Which is essentially just this PDE here. So I end up with, this is equivalent to 0, okay? So moreover, remember E of 0 is going to be equal to the integral from 0 up to 1, the half out front of w of x0 sub t squared, right, which is 0, plus c squared k of x w sub xx of 0 squared dx. This whole thing's also equal to 0. Okay, so this implies that E of t is equivalent to 0 for any t greater than or equal to 0. So this implies that wt and wx are equal to 0 for any t, and for x from 0 to 1. So this implies that w is a constant, okay? And then because w of x0 is equal to 0, this implies that w everywhere is equal to 0. So this implies that u1 of xt is equal to u2 of xt, and indeed we have uniqueness. Okay. All right. So you might say, well, where the heck did you come up with this energy function here, right? How did you know to use that, right? So one way is to kind of work backwards from the PDE and figure out how you're going to be able to use the PDE, okay? So to get that energy function, okay, note the following, that the original PDE times ut is what? Well, it's going to be u sub t utt minus c squared u sub t k ux x, right, is equal to 0, okay? So this implies that the derivative with respect to t of a half the integral from 0 to 1 of ut squared dx minus c squared integral from 0 to 1 ut k ux x dx is equal to 0, right? Working backwards. This implies that if we integrate by parts, right, we get e dt a half integral from 0 to 1 ut squared dx minus c squared ut k ux evaluated from x equals 0 up to 1 plus c squared integral from 0 to 1 k of x u sub x uxt equal to 0, okay? And so, right, so for our original equation, we have that d dt, a half of the integral from 0 to 1 ut squared dx plus d dt c squared over 2 integrated from 0 to 1 k of x u sub x squared dx, right? So sort of going the other way. This is equal to 0, okay? So that implies that, well, if I want to use something like energy conservation, that this energy that I can define, okay, is conserved, okay? So how to cook up an energy function? Typically, you expect to have, some leading term here, right, that you're going to have to multiply through. It's not always necessarily going to be u sub t. It could be, u sub xt or something like that. And that should give you the derivative of the energy function that you're interested in when you integrate over the domain. Because remember, it's a functional, and you would like, to be able to pass a function in and have a number come out. Okay. Some final remarks, okay, on Sturm-Liouville theory. Okay, so it gives a basic, okay, needed ingredients, okay, to apply separation of variables to a wide class of problems, right? Not just homogeneous problems, right? You can use homogeneous problems, and as we showed before, not just constant coefficient problems. It also works on variable coefficient problems. So most of your second order PDEs that you come across from these physical laws, you can apply them to for linear problems, right? And the key is really completeness of your eigenfunctions, okay, and orthogonality of your eigenfunctions, right? In addition, properties of your eigenvalues are going to affect the time evolution, okay? So that's why for a lot of problems, right, you're interested in what's called the spectrum of your linear operator, which is going to include the eigenvalues, which are sometimes called the point spectrum of the linear operator. That essentially tells you, anything that can be passed through that linear operator, what's going to happen to it is given by your set of eigenvalues. So if they're all positive, okay, that gives you information about whether you should always expect growth or decay of your solutions, as we've shown. Okay, so so that concludes for now our discussion of separation of variables. We'll actually circle back to it when we talk more about solving the Laplace and the Poisson equation. Okay, I want to move on now to the next